All right, hello everyone. So today we're going to be focusing on modeling once again. So especially how do we show heat transfer? How do we show energy in our substances? So this is what we've been practicing. So it should feel pretty familiar if you've been here, or if you've been absent, then perfect. But this is the time to kind of catch up on some of these skills. So we're going to kind of just go over and review like the different things we've been talking about. How do we effectively show heat and energy transfer? Um, so just the different ways to show that we've been talking about. And then I'll give you a new situation in which I expect you to create a new model. So this is going to be focused in our workbook. So if you don't already have that, grab it right now. We're going to be focusing on page 4, starting off, again, just going through our ideas that we've been doing. Throughout this, whether you're watching this later on your own or if you're watching it in class, the substitute can pause throughout. So a few times, like throughout this, I'm gonna just say like, all right, pause the video and try this part on your own. And so I expect y'all to do that, your best with that. And yeah, so let's start off with summarizing how do we model. So there's kind of two different things we might want to show with modeling. Sometimes we want to show something macroscopically, and sometimes we want to talk about something submicroscopic. And I'll explain what I mean by those words in a sec. But depending on what our model's for, we might want to show different things. We might want to show a different scale. So let's think about macroscopic first on this page. So I haven't used this word before, I don't think, but what I mean by that, you guys know like microscopes, right? If I want to use a microscope, micro means really, really small. So microscope, we're looking at small things. Macro is the opposite of that. So macro means not small, like big. So if I wanted to show something at the macroscopic scale, if I wanted to show like the interactions with that lens, we would just be making a drawing, a model of something we can actually see, something we can see with our eyes. Okay. So we have an example of a macroscopic model in this picture we have here. So let's do some practice with what that would look like at this scale. So not a trick question. If I put an ice cube in my hand, what would we expect to happen? And then thinking about what you'd expect to happen, is that a physical change or a chemical change? So take a sec, pause this video. I want you to work on these two questions. What would happen? Is it physical or chemical? Explain to a friend. Try it on your own. Welcome back. You definitely paused. I believe you. So now that you've tried it, not a trick question, like we'd observe it melting, right? Chemical versus physical. So reminder on this, it's been a sec since we've talked about this. But since it's a phase changes are physical changes. So no, and keep it in your own words if you wrote something else, but just to clarify in case you didn't get it, no chemical change. Water and ice are both H2O. So only physical. Okay. So you might have wrote it different, that's totally fine, but just to make sure we got that point. We're not actually observing a chemical change, but we did observe this physical change, different states of matter. All right. And then, so on this model, we already have like a basic structure of this, right? We want to model how heat moves. So if I want to show the direction of heat transfer, how would we show that? So we've already been talking about that in class, right? We've done a few examples of this, but if I specifically want to talk about the heat transfer going on, I'm going to want to use squiggly arrows or wavy arrows, whatever. I'll call them squiggly. something like that. Okay, so that's, if you choose to do something else, again, just making yourself a key, it's totally fine. But how I'm going to do it is with these kind of arrows. So again, let's pause for a sec. I want you to think about, how would the heat be transferred in this scenario? Would it go from ice to hand, or from hand to ice? And can you show that visually? Let's take a sec. Try that. And hopefully we all feel comfortable at this point that because your hand is warm and the ice cube is cold, and we observe this physical change happen, there's energy coming from your hand into the ice. So we'd want to draw wavy arrows from the hand into the ice. Okay. So that could be a model at the macroscopic scale, at the visual scale. But so not actually showing the particles, just showing that interaction. But sometimes, it's chemistry class. Sometimes we care about the molecules, sometimes we care about the atoms. So sometimes we're going to want to make a particle model. A different way of saying a particle model, we're talking about the submicroscopic, so even smaller than what is with a microscope, so what we could never actually see. But we want to draw the particles. Okay. So again, something we've been practicing, but sometimes we would want to show the particles. And again, we've been talking about this, but we want to show the differences between different particles, and how they're going to interact. So we've talked about this before, but let's see a good visual of this. So I am going to open this simulation, and as we look at this, I want you to fill in these questions. I'm going to heat it up. I'm going to cool it down. I want you to write down your observations on what happens to the particles. And then we'll work on making a model of that, okay? So let me open up the simulation. So we just got this box, and I'm going to add some gas to the box, and the particles are going to move around. Again, we might represent particles with simple shapes like circles, and they're just filling the box, moving around. If I want to show a gas, it's going to move around and fill my entire box. It's not going to sit at the bottom or anything like that. So cool, we're seeing this. Okay. And now I want you to write down your observations. I'm going to add heat. What is happening to our particles? Okay. I'm going to take that heat away. I'm going to cool it down. What are you observing? Record your observations for our particles. Okay. So hopefully we're all seeing the difference. If I was there in person, I'd ask you guys what it is, but hopefully we're seeing, when we're cooling this down, they're slowing down. When we heat it up, we're seeing that they move faster. So if I wanted to show a cold gas versus a hot gas, again, what we're observing here and what we've been talking about is the concept that temperature is very closely related to how much my particles move around. So if I was to show a cold gas, so I'll just add I don't know, 5 circles or whatever to my different boxes. Again, both gases, both spread out, both moving around. But we observed that the cold gas is going way slower than the hot gas. So again, we've done this before. So maybe pause for a minute. What would you add to these pictures to show that difference in temperature, that difference in motion? Okay, and as we've been talking about, hopefully we added some arrows maybe, or something like that. So for my cold gas to show that it's going slow, I'm adding some arrows to show that it has motion, show that it has temperature, it has kinetic energy, but not that much. versus when like we saw, hot gas has more kinetic energy. So to represent that change, I choose to do big arrows. You could do like thicker arrows, you could do more arrows, something like this. Okay. So as we're thinking about these models, if there's a difference in temperature, that's going to be important for us to represent using these different conventions, these different strategies, because difference in temperature tells us a lot about heat. Okay. And we've talked about, like the first day we talked about this as well, but let's make sure we have a record of it. If I want to show a gas, it should fill container and have the most, I'll say, movement. I'm not gonna spill this whole space, but you could paraphrase, but we've seen this before. If I have a gas, we'd want to make sure our particles look like they're all super spread out, that kind of thing. If I have a liquid, they'd be closer together, a little less movement. Just for the sake of space, I'll just say solid, but know that liquids in between. Condensed, I'll say. So dense, like all together, like we've talked about. Okay. So if I was comparing a solid to a gas, it should look very obvious in your model. All right. So like we just practiced, if I want to model particles, we got to make sure we show those differences in temperature, differences in motion. And what I'm going to always do is using straight arrows. So you can see that the arrows are going in different directions. And we can see that there's, by the difference in the size of those arrows, we can also tell the speed of our particles. And like we've talked about, longer arrows represent that they are moving faster, they're moving more, while shorter arrows are showing that they are moving slower, moving less. Right? So again, just kind of a summary of what we've been practicing with. The new scenario you guys are going to start to work with today is described right here. What I have, this afternoon, I got some hot water and I put it in a coffee mug and I put it in this plastic bottle with saran wrap over the top because I couldn't find the cap. But both of them, and I sealed them both, and they've been sitting here since the afternoon. And we're going to see how their temperature is now and model that. So first of all, let's pause our video and I want you guys to predict what you think will happen to temperature and happen to heat in this scenario. What do you think is going to be the difference? Make a prediction. All right, now that you guys have all made your predictions, let's gather some data. So when I put the water into these two cups, and I'll just write this here, I'll give you a spot to write it later, but let's just lock in for recording some data. Both of them had an initial temp of water. I filled them both with like 500 grams of water, same starting temperature. But let's measure what is their temperature now. So just gonna pop off the lids on these guys. And here's my thermometer. Give it a sec. Looks like it's stopping at 21.8 degrees Celsius. Okay. And I will then take my cup, measure its temperature at this point. So after a few hours, looks like it's sitting at 37.7 degrees Celsius. Okay, so maybe it matches your prediction, maybe it doesn't. But that's our data that we're going to be working with here. So our goal with these next few pages is to be able to model that difference and describe what's happening in this system. So just a note before we start, let's think about our systems here. We learned that there are 3 different types of systems. We have a open system, a closed system, or an isolated system. Or sorry, yeah, isolated system. So how about you pause for a sec, tell the person next to you, what type of system are we working with our bottles here? What do you think? Okay, hopefully we're thinking maybe that they are closed systems because they both have a lid, so we know they're not open systems, but they both experienced a change in heat. So they both must be closed and not fully isolated systems because we saw a difference, a change in temperature usually represents that there was a transfer of heat, okay? So these are both closed systems, just different closed systems. Let's try representing what we know so far. Okay. So let's look at our models here on our next page. So let's do our plastic bottle first. And let's just kind of summarize our data in here. So surrounding temperature. So what is the temperature of the air in this room? Sorry, should have had you guys define our system, but since we can't have a conversation about it, I think it'd be helpful if we just define our system as our bottle and then the water inside the bottle. And then our surroundings is going to have interactions with our closed system is the air. Okay, so surroundings, that would be like our room's temperature. So looking at my thermometer I have up there, looks like our room is at like 22 degrees Celsius. I guess I could use this one too. Yeah, 22 degrees Celsius. So that's about what it was this afternoon and still what it is, and what we're going to use as our comparative spot. And we said that for the water bottle, our initial temp was 85.3 degrees Celsius. And we saw that our final temp was 21.8 degrees Celsius. So this is our initial temp. So it was after, let's say after 0 hours had passed at the beginning. And then this is what it looks like now. It's been about 3 hours. So that is the difference we're looking at. Again, let's just do our data first. So same room, they're both these. I didn't have a hydro flask, so pretend. But it's gonna work pretty similar. We got our coffee cup with 22 degrees Celsius, right? For the room temperature, again, same starting temperature, 85.3 degrees Celsius after 0 hours, but a final temperature of 37.7 degrees Celsius after 3 hours. All right, so let's try and do some modeling. So things that we're going to keep in mind here, have them written out here, just to give you another list of it. Yeah, well, yes, we already talked about this. We'll talk about that in a sec. So as we practice with our models, and I'll bring this slide up for you again in a sec, but we want to make sure we're showing motion, aka which will help us show difference in temperature. We want to make sure we show heat transfer, and we want to make sure our heat transfer shows is the heat going from this thing to this thing or from this thing to this thing. So the direction really matters with that heat transfer. and we'll talk about the amount of heat transfer in a sec. And just make sure it's very clear to your viewer that you're talking about two different substances. If there's any interactions between them, make it key. When in doubt, like explain it to your viewer to make sure that that's super clear. So let's try our models. So I'm going to do the initials with you, and then I want you guys to work on your finals. Okay, so let's do our initials. So I want to show a particle model. So I asked for particles. I will be clear when I want you to do that. So let's just draw our bottles. So inside of our plastic water bottle, there is the water molecules. Those are probably pretty important because that is our hot water. So I'll draw all my water molecules. Probably can draw them differently if you want, but yeah, something like that maybe. And we want to think, remember, this is our initial pretty hot water, right? So think back to what we just did. If I want to show that these are hot molecules, I want to show that they have lots of motion. So we're going to see something like this. So long arrows to represent that these are hot molecules. Okay, and then we observed that there was a temperature change. So a temperature change helps tell us that there was an exchange of energy, an exchange of heat. So that means that there must be some interaction between our system, the stuff on the inside, and the surroundings, the stuff on the outside. So if I want to show an interaction, I want to make sure I show my other particles. So I'm going to show my air particles surrounding. I'm just choosing to do different shapes, so it's obvious that they're different. Okay. And we want to think about showing temperature differences if there are any, and then showing heat transfer if there is any. So when I think about my air temperature, this temp, versus my water's initial temp, is there going to be any difference in these arrows that I drew? So, think about it for a sec. Would there be any difference? How would these molecules look different from these ones? And hopefully you're thinking, well, these ones are at a lower temperature, they're colder. So I want to show them with less movement. So I'm going to want to make sure that my arrows are much smaller on my air, my surroundings. Okay. And in this plastic water bottle, we have this clearly defined system. We have these walls, but there must be this kind of interaction with our surroundings, right? So everywhere where the water touches the plastic bottle, all around this perimeter, I don't know, this outside part, there can be direct interaction with our air. So every time like an air molecule that comes in, like bumps up against my water bottle, there could be some kind of interaction here. So we want to think about what would the heat transfer be involved with that process. So, again, pause, think about it. When I have hot water in here and then cooler air surrounding it, what is heat transfer going to look like? How would I show that? Which way is it going to go? What are we thinking? So hopefully we always want to show heat transfer from the hot thing to the cold thing. So heat transfer from the hot thing to the cold thing. So squiggly arrows out of my water bottle into my surroundings. So these might look different for each of us, but something like this. From the bottle to the surroundings. Because whenever there is a temperature difference, we're going to see heat transfer. Whenever things are in contact and we see a temperature difference. All right. So that's what our initial would look like in the plastic bottle. Let's do our initial for the coffee cup, and then you'll get some time to finish up your models. So let's look at our initial for the coffee cup. And first we should kind of talk about like how the heck do these things work? So maybe you guys know, like if you ever had like a Hydro Flask or any like fancy water bottle like that, any of these metal ones, what is really special about them is they have something called a vacuum seal. So maybe we've heard of vacuum seals, maybe not, but let me show you a picture of what it would look like inside like a Hydro Flask or something. And this is not letting me go backwards, which is super cool. That's fine. I'll just open it here. So a vacuum seal, what does that mean? So a vacuum means like no air. So what actually happens? So this like there's some like YouTube channel where they like slice things in half. So this is what it looks like inside like a hydro. So as you can kind of see, there's not just like the part where whatever liquid you have in here, water, the water is touching the inside metal, the inside of the container, but it's not actually touching the outside of like the surroundings because you can kind of see that weird gap. So there's kind of two layers of metals with a gap with air or like minimal air in between. So why is that helpful? Let's kind of think about that. So here, let's see again with this drawing kind of shows it too. So we're gonna have our water, again, hot water. So I'm gonna fill up my water bottle or coffee cup, whatever, with hot water. So showing very large arrows, lots of motion, lots of heat, or sorry, lots of temperature, I guess, more accurately. And I still have my air that is still 22 degrees Celsius. So much smaller arrows on my air. Spread out kind of everywhere because it's a gas. Okay. So same starting situation, but what is going to be different about our heat transfer? So this is kind of weird. That's why I wanted to like do it with you. Thinking about our system here. We talked about yesterday how it's really hard to actually have like a perfectly isolated system. The only way to be perfectly isolated is if after 3 hours or like after infinite time, it was still this temperature. But that's not the world we live in. But it did do better at not going down in temperature that much. So let's kind of see if we can model why. So the type of heat transfer that we've been talking about needs contact, right? That very first day when we put the ice cubes on the block, we need to have the contact between the two substances in order to have heat transfer. So if the air from outside the surroundings isn't actually making contact, isn't actually bumping into the walls of the water, there's not going to be as much heat transfer going on between those two things. So what is happening instead? Because we did still see a change. So maybe you want to take a sec, come up with your own theory. The main reason we do see some heat transfer is because the heat from the water gets absorbed into like the inside metal. Here, I guess you probably aren't gonna be able to see this, but like the heat from this water gets absorbed into this inside metal. And then that inside metal absorbs from the heat. And then from that, this inside metal is touching like the lid and stuff. So it's not perfect. There's going to be some heat escaping, but there's much less contact with the outside. So our heat transfer is going to look different from our other scenario. Still going to be some heat transfer because we observed a change in temperature. And there is some contact between them. Here, I'll draw more air up here just so it's clearer. But less. So we should make sure that these arrows are smaller or there's fewer of them, something like that, to show that the heat transfer is less from what we saw in our water bottle. Okay, so what I want you guys to do is basically complete the rest of these 2 pages. So thinking about how would it look different? So like focus on one thing at a time. The plastic bottle. Would any of my arrows look different? Would my heat transfer be any different? Would my motion be any different? How would it look different under these conditions at the end? And then I want you to describe the change you drew. So why did you change the size of some arrows or something like that, the number of arrows? Or why did you not if you chose not to? So I want you to explain what your model is showing. Same thing for the other scenario. Describe what you're showing. How is heat moving? And then I want you to use some evidence and put it in your own words. How, or explain this data that we saw. Why was there less of a temperature change in this scenario versus in this scenario? Okay, so for the next chunk of time, I want you guys to work on these 2 pages. Or I'll just keep talking, I guess. If you get done early, then you can work on PS 5.1, okay? But that's it for our little check-in video. Make sure you're being thoughtful about your model, including all these details, explaining what you're trying to show. Because on Monday, I am going to want to check in with you guys and see some progress and these completed models so that we can touch in about them. Okay. But the rest of the time is yours to work on these 2 things. And have a great rest of your Friday. See you guys later.